postdoc at IIS. I did his PhD in Cambridge with Hanno. I'm going to talk about two different topics today. So it's
Thank you. So we've actually been office mates in Kepler today at the same time. Yeah, so nice to be here. Thank you very much. I'm going to talk about two things. I hope I'm going to talk fast enough, so I'm going to get to the first one, because the second one is one I'm actually really excited about, how to make an extra solar planning catalog that has all the good things that you know about open source and incorporate that into a catalog of astronomical boundaries. But I'll start with my main research topic, which is the stochastic migration of planets. And I'll start that by a quick overview of extrasolar planets about the census that we currently have. So I'll show you a picture of all discovered extrasolar planets. These are all as of today. There are 869 of them. There are all kinds of different planets in there. A lot of them are very massive things, and mostly the green dots here. These are things that are much more massive than Jupiter. They have multiple Jupiter masses, sometimes 10, maybe even up to 16 Jupiter masses. And then it goes all the way down from normal Jupiters. A lot of them are close in orbit, small Jupiters, Neptune, super Earth, and then Earth-sized planets. So there's really a huge set of different kind of planets we find in. Now the ones that I want to talk about is a subset of those. And these are those. These are planets in multi-planetary systems. So planets with systems with more than one planet in there. And as you can see, we find already quite a few of them. Most systems so far are not multi-planetary systems, but this will change very soon. There are also different kinds of systems that we find. Most of them have multiple Jupiter mass planets in there. That's because radial velocity surveys tend to find these very easily. So multiple big planets on wide orbits. These are the green dots that you see here. There are usually two of them. Then what we see now with Kepler more and more is densely packed systems of really close-in small mass planets. These are systems like these here, where they have all kind of similar mass. They're kind of Neptune size, or super Earth, Earth-like sizes. These are the ones that are popping up now. But so far there's only one solar system in it. I'm not sure if you can figure it out which one of those dots represents the solar system. There's only one of them in there. Any guesses? I'll tell you, it's that one over here. The colors correspond just to the size. The color is the size. So the solar system is the only one that actually has all the different sized planets in one system. So we have Jupiter, Saturn, we have some Neptune-sized planets, and it goes all the way down to these terrestrial planets. That's something we haven't seen yet in extrasolar planets. They're usually very similar size in one system. So we're still special in that respect. Now some of these systems are in resonance. I'll talk to this in the next slide more, and most of them are not. So if you talk about multi-planetary systems, you can do a lot of things that you can't do with single planetary systems. And one of them is you can look at the correlations between the periods of these systems. So one way to look at this is look at the period ratio distribution of all these planets. And this is a cumulative distribution. What I'm doing is I'm plotting all period ratios of two neighboring planets. Okay? Like for the Earth and Mars, you would take the period of Mars and the period of the Earth and divide the two numbers up by each other. And then you do that for all the systems that you find for all the planets, and you make a cumulative distribution out of it. If these planets were completely random distributed, you would see no features in this plot. It would be a smooth line. Okay, now there are correlations. And there are strong correlations near integer ratios. And that's what you see here, for example. There's a bump near an integer ratio of 2 to 1. That means that there are a lot of planets which go around once, while the outer companion goes around twice. It's almost an exact number 2. That's a resonance. These systems are in resonance, the mean motion resonance. The strongest feature is here, 2 to 1, but there are other features here, which is an integer ratio of 3 to 2. There's the transition system with 4 to 3 resonance. And you can see higher order resonances in down as well. This is the main kind of result by looking at these multi-planetary systems. What you can see, there's a lot of structure in these. There's a lot of information that you can dig out and try to understand. And I want to explain this kind of distribution for different sets of planets. Now these are for all the discovered radial velocity systems. And radial velocity method is very sensitive to detecting high mass planets. And that's why it's biased towards those. But you can still nevertheless see a correlation between mass and the architecture of the system. You can see that I colored the points according to the planet's mass. And the more massive planets tend to be in resonance, whereas the lower mass planets are not in resonance. And this is only for the radial velocity sample alone. So this was the state of the art a few years ago. And then Kepler came about. Now you have many more planets. Okay, so these are all the Kepler planet candidates, not including all the other ones that you already know. And there are thousands of them. Okay. And one thing that you see is, well, first of all, there are a lot of planets, but they're all much smaller mass than the other ones. Okay. These are mainly the red dots, which are some Neptune, super Earth, or Earth-like planets. And there are only a few of the bigger ones in terms of Jupiters. So these are not confirmed planets, and some of them might turn out to be false positives, but most of them probably will be real planets. So I'm going to look at this sample too. And I'm again looking at the multi-planetary systems, and that's the subset that looks like this. Most of these, as I said earlier, most of these multi-planetary systems discovered by Kepler are densely packed. Small mass systems in closing orbits, something very different from the radial velocity survey. You can do the same period ratio distribution plot that I made before, but this time for the Kepler planets. And what you see is a curve that looks much smoother than the other ones. And it's not only smoother because there are more planets, it's smoother because there are much less features present in this distribution. So these planets are more randomly distributed than the more massive ones that were discovered with radial velocity. Nevertheless, you can still see features at those precise resonances. Here's the 2-to-1, 3-to-2 resonance, and you can see that there is a feature. And in fact, there's a deficiency just about where the resonance is, and there's a pileup just outside the resonance. So this is now what we can do with Kepler. We have much better statistics. We're probing a new parallel regime with much smaller mass planets. We can really try to understand how we can form systems that look like these in a statistical way. And that's the new thing. So my take on how to form this system is via stochastic orbital migration. That's the point I'm trying to make today. So let me explain to you how that works. Before I do that, I'm going to explain to you how normal orbital migration works in just a few slides. If you put a planet in a protoplanetary disk, it starts interacting with the disk. And it will create a spiral wave. It will create one that goes upwards, create one that goes inwards. And there's a slight asymmetry between those two waves. And that creates a torque onto the planet. So the planet will move around because of this torque. This is a complicated process, and we can't really claim that we fully understand this. It depends on a lot of thermodynamical properties of the disk, like the density gradient or the temperature gradient. And if you change those slightly, you can change the asymmetry of these weights, and you can change the torque quite dramatically. So the only thing we can really say is that planets will move. They will move around a lot, but we don't know how fast or which direction they are. We can estimate the migration rates, and with type 1 migration, it's relatively fast. It's usually shorter than the lifetime on the disk. So you somehow need to stop these planets before they migrate into the star, otherwise you'll lose them. And there are a lot of ways to do that. But the migration rate is relatively fast. And if you have more massive planets, then another effect kicks in. You open gaps in these disks. That's what you see here. I put a Jupiter-sized planet in a minimum mass solar nebula kind of disk, and it will create a gap. It opens. It's so massive that it can locally perturb the density of the ring of the disk. In this case, the migration rate is much slower, and you migrate into type 2 regime, which basically follows the viscous evolution of the disk as the disk is on the star. So these are the two well-known migration regimes. But the question is, how does really a protoplanetary disk look like? And this obvious conception, I think, kind of tried to mimic that. If you look here, you see that it's not really a smooth disk. It has a lot of fluctuations in it, and it's turbulent. And there's a very simple argument for why these disks have to be turbulent and not as smooth as the original movie showed you. And that's because you can measure the angular momentum transport of the disk onto the star, and it's much higher than what you would expect from a molecular viscosity in the gas itself. So there has to be some component that is a turbulent viscosity. And this viscosity could be created by a range of instabilities, but most people think it's most likely weak is the magnetorotational instability. It's an instability that can occur in magnetized disks, and the surface density looks approximately what's shown in this animation here. No matter what instability you have, we will always create some density perturbations in the disk. And these density perturbations will interact with the planet that's embedded in the disk gravitationally by exchanging forces. Because it's a turbulent medium, it will undergo a random walk in the end. These forces are stochastic, so the planet will undergo a random walk. It's important to note that, again, we don't really know the precise strength of these forces. We know that they have to be there, but where they saturate and whether there's a dead zone in the disk and all these kind of things are complicated and they're very model dependent. So it's hard to put them all in a self-consistent model. But we know that they have to be, we can approximately characterize the strength, but it's not written in stone how the precise number is. When a planet undergoes a random walk, this is how it looks like. It undergoes a random walk in every single one of its orbital parameters. It's not only undergoing a random walk, energy and angular momentum, all these orbital parameters undergo a random walk. Okay? And even though every single random walk is a stochastic process, we can't describe it. We can describe the ensemble average of how these things work. And we can do this analytically. So these equations here are diffusion equations. There's a diffusion coefficient d and a time t. You can see that all these quantities grow like the square root of time. That the root mean square value grows like the square root of time, like it should be for a random walk. You can do that analytically for all these orbital parameters to compare it with simulations, and they fit quite well. The most interesting thing is to do the same analysis for multiple planets. If you look at multiple planets and see what happens to those if those are stochastically forced, you can learn much more than by looking at simply the single case planets. For two planets, the thing we're looking at are the resonances. That they are the most interesting dynamical character properties. And we're starting out from planets in resonance, and we're trying to estimate how long does it take for these planets to leave the resonance, to break out of this resonance. And that's what you can describe also with a diffusion equation like this one. It looks a bit more complicated, but it's simply, again, a diffusion coefficient. You have a quantity, in this case the resonance angle, which grows like the square root of time. And it depends on the diffusion coefficient, on the strength of these forces. And again, you can compare it with a numerical method, and it agrees very well as long as the sampling time scale is long enough. Yes?
When you do these calculations, there's no standard migration built in, or just the quarks and the gases. It's just the turbulence.
They're usually both components.
Oh, okay. And so the turbulence always dominates?
It depends. So there are different processes, right? One is a linear trend. So it's like a Fokker-Planck equation. One is a smooth migration, always moves inwards. So on average, you will always do what the smooth migration will do, but on top of that, you will diffuse around that value. So it's kind of hard to say which one dominates. They're both equally important. They just describe two different things.
Can I ask about eccentricity?
Yes.
So eccentricity is done very fast in Python.
Yes.
Right.
So, but you still find the same interactive sites with eccentricity is still
Oh, well, there is no eccentricity damping in here.
Oh, okay.
In that one, yes. You would saturate at some point, yes.
Okay.
In that case, yes.
I guess by population participation, I think you might think that the center of energy of the planet is your related energy single spirals, naturally the MRI, some spirals together.
But the damping is not by the same mechanism that drives it, so you can't use that theory.
Well, no.
The damping is by smooth spirals.
Yeah.
So if the driving and damping is both smooth, by the turbulent energy is right.
No, because of the energy planet energy.
Okay, so these formulas are the ones that describe us how long these resonances are lived. Okay? And we can simply put in some standard parameters and see how long do we think planet systems in mean motion resonances survive. And the answer is that for a system like GJ876, which is a very massive system on a very close in orbit, has been discovered by radial velocity very early on. So this is really the prime example of the system in resonance. This system is stable for 10 to the 7 or 10 to the 8 years. You have to look at where this number is 1. This is the strength of the migration force. 1 is probably the most realistic one. And this tells you the lifetime of the resonance. So GJ876 is even off the chart. So it's very stable. There's nothing that can disrupt this system. If you go to an Earth-like planet, it looks very different. If you have two of those in a mean motion resonance, you're likely to disrupt them within just 10,000 years. They're not going to survive. And already from first slide, that's kind of consistent with the picture that I showed you earlier, where these more massive planets tend to be in resonance, whereas the lower massive planets are not in resonance. So all of this makes sense. And just one thing I want to point out that you know, this was actually published in a paper from 2009, so we didn't have the Kepler data at this point, but it turns out to be consistent. Okay, so I want to talk about one system in particular. It's Kepler 36. Kepler 36 is a really exciting system because well, the orbits are extremely close. If you would stand on Kepler 30b and you would look out in the sky and see Kepler 36c, the planet would be this big. Okay, this is the moon, so it's much bigger than the moon in our sky. It's because these orbits get extremely close. And this planet is not orbiting this planet. It's another planet on another orbit. It just comes by really close. I think that, yeah, it's just really amazing. This system is near a 7 to 6 motion resonance. It's not exactly in it, but it's very close to it. So it suggests that the resonance has something to do with information. Maybe the most interesting part is that these densities of these two planets are very different. One of them is a rocky planet, and one of them is a rocky planet with a substantial hydrogen-helium atmosphere on top of it. So they have very different composition. They're almost on exactly the same orbit. They get very close, and it just brings it really suggests that these planets formed in different regions and then got somehow closer together. At least that's my interpretation.
Let me just take a comment. I think Jim has a scenario, mentioned scenario explaining those very different ways that works together.
Yes, well, so you can start off with both having significant hydrogen flows, and then one of the planets losing it. Yes. People can start later.
Yep. So now, if you want to form Kepler 36, and this is in general, this works for all these systems. If you want to form it in a protoplanetary disk, you have migration. All that matters is how fast you migrate them together and what's the masses of the planets. If you have those two quantities fixed, you can almost, with a one-to-one relation, end up with one specific resonance that is forming. And that's shown in this plot. This time is evolving upwards, so I'm integrating all the information upwards in time, and I'm varying the migration time scale on how fast these planets are moving around. Okay. And they're migrating very slowly. They will capture into resonances that are very weak, and the outer ones are weaker. Then if they migrate faster, they can jump over them. They get into closer resonances that are much closer together. So that's what you see here. For slow migration rates, you end up in resonances like 3 to 2, where the period ratio is large. If you migrate faster, you end up in higher and higher order resonances like 4 to 3, 5 to 4, 6 to 5, and 7 to 6. Now this system's Kepler 36 is somewhere around here, around this period ratio, 7 to 6. So you need a migration time scale of 1,000 years. And that's the problem here. If you want to have a migration time scale of 1,000 years for these super Earth-like planets, it's very hard to migrate them this fast, even in a type 1 migration regime, and even though we don't understand the details of the migration very well. 1,000 years is very large. It's a few orders of magnitude faster than what people usually assume. So we need to have a different way of getting them in these high order resonances. And one way is stochastic migration, which very easily can give you higher order resonances. It's the same plot as before. Time moves upwards, but now I'm varying the amplitude of these stochastic forces. I told you we don't really know how strong these forces are, but these are kind of realistic values. And what happens is that with no stochastic forcing, you end up in these high order resonances, with these low order resonances, 3 to 2 and 4 to 3. They remain stable for a very long time. If you turn it down to 0, they remain stable for the entire lifetime of this. For some realistic values, though, what happens is that you break the resonances fairly early on in the evolution of the system, and then you end up in higher and higher order resonances. This is the blue region here. The blue region is close to the period ratio where Kepler 36 is observed in. Now the interesting thing is that this is a stochastic process, and you can see that it fluctuates a lot. The period ratio is not a constant, so you constantly jump between different resonances back and forth, and it's not a simple as simple as in the non-stochastic migration case. But you never leave the system either. You don't scatter these planets off. They don't get unstable. They end up in these closely spaced orbits, but they remain stable, having a low period ratio for the entire duration of the simulation. Only one of them got scattered around and we lost the planet. Okay.
You don't get noticed.
No. just happens that the stochastic migration together with this damping that's still present from the disk really has a sweet spot for opening up this parameter space where they stay in. And it's not trivial to find a stable solution for these space planets. If you would just randomly place them, they would most likely be lost within a very short amount of time. So we think that this is really one explanation for this Kepler 36 system, and it's kind of representative for how the Kepler systems in general might form. Just one of those simulations in CITA. If you think about a case where one planet might form further out, one might form further in, you migrate them together, you end up in the first resonance, it gets unstable, they get close together, and so on. And you end up in this high order resonance, which then makes it to the end. This is a fairly smooth case. There are more chaotic ones.
So they're at what? I mean, that's about 0.08.
Yes, I don't remember the distance of the current system. Okay. But you can see that at the end it's kind of self-similar. It doesn't vary much anymore. Once they're in there, they kind of just get closer together in a self-similar way. And I'm not modeling how they stop.
Do you model the eccentricity? Because the current eccentricity is almost exactly zero.
I do, and we're very close to that.
You do have zero eccentricity also.
Yes.
But you need fairly rapid migration here, so it's very important that they do stop.
It's still fairly rapid. It's something like 20,000 years, which is a factor of 20 better than the 1,000 years would normally need, but it's still fairly rapid. Yes.
So sorry, what are the masses?
I need to look at it.
The outer one, I think, is 8, and the inner one is 4.
Okay. We have 4.3 and 8.
Showing up there.
Okay, so this is one way to form the system. It doesn't mean that it really has to form this, but all these parameters that are chosen, the migration rate is fairly fast, but the stochastic migration amplitude and all these things are fairly natural scales that don't have to be fine-tuned. And you can see that in the last plot. The fine-tuning is not an issue. This is really the sweet spot that's picked out by this kind of method automatically.
Can we understand the physical scale of these stochastic forces? So what is that exactly? Density calculation?
Yes, so it's scaled with respect to a certain minimum mass solar nebula profile, and then we take a quantity of 1 would be 10% density fluctuations of the order of the scale height. The size is the scale height, and you have 10% density fluctuation in that block.
10%. So that's 10%, right?
That would be here. No, that would be 1 in those units. And then we reduce it. So these are all weaker because maybe the turbulence is in a dead zone, or you have only active in the top layers. So all these things reduce the amplitude. So this canonical value of this 10% is here, and then this is probably what's more realistic. It doesn't change if I use the water.
So you have multiple scale height groups within the result? I mean, this is just one cube that has density fluctuation, or you have multiple?
No, it's a distribution.
It's a distribution
Yes.
around here, and that's
Yes.
just the instruments.
This only sets the scale, and then you set the time scale, which is something like the orbital time scale. And this completely describes the statistical properties of the force that I did. Okay. So just quickly, you can do this in a statistical way, and I've just scratched the surface on this. This is by no means the end, but this is the distribution that you want to explain. Okay, this is a period ratio distribution, and the question is, does this stochastic idea kind of reproduce something that looks similar? And the idea is yes, it does. So what I'm doing here is I'm taking the observed masses and the observed architectures of these systems and placing the planets not in the current position, but further out and slightly further apart in the minimum mass solar nebula, and then turn on the smooth and the stochastic migration forces and let them evolve forward in time. And it's a really simple model because you don't need to synthesize any planet. I'm taking the observed planets. Okay, there's no population synthesis model that needs to explain where planets form or how many of them form, just taking what's observed and then integrating them forward in time. It has some shortcomings as well, I'll mention in a second as well. This allows us now to do two things at once. We can look at the statistical quantities like the period ratio distribution, the eccentricity distribution, and maybe even things like the transit timing curve distribution in this artificial ensemble of planets that are forming. But we can still look at individual systems, like this Kepler 36 system. That's still going to be in there somewhere, and it's hopefully going to look similar to the observed one in one way or the other. So you can combine two things. And the results look promising, I think. What you see is the observed distribution in red, that's the one I showed you before. And now the other curves are coming out of this model. And they are similar, they're not identical, but they have very similar features. Overall, you can see that there are very few features, but the features are present still where these inversion resonances are. There's the offset of this bump near the resonance. It's the right direction. It has approximately the right amplitude. It's not a perfect match, but it all goes in the right direction.
How do you measure the mass?
Just by the radial. Yeah, which might have larger errors, and it might depend on there are a couple of things I'd like to do. First of all, I'm using a fixed nebular profile in the background. It would be nice if that were self-consistently integrated forward in terms of kind of 1D hydrodynamics model case. The other visual effects I'm missing is tidal damping, which is probably important for at least some of these planets around very close in orbit. It can't explain the entire distribution, but it might be important for a few of those systems. There's a completeness issue. So Kepler is not seeing all the planets in these systems simply because it's a geometric effect, or maybe some transits are just too weak for some of our larger periods. So I'm missing planets in this ensemble. And if I'm integrating the R effect of the system without having these other systems there, it might really screw up things. So you can correct for that, and I'm trying to do that later. And then it would be nice to move to something GPU based where you can really run a lot of them in parallel and really explore the parameter spaces much more than did before. Okay.
Before you go on, can I ask a question about period ratio distribution?
Sure.
So this one, is an observed one that's uncorrected effect, as you said, continuous.
Yes.
So when you actually correct for it, if you try, you get much steeper, meaning almost everybody is having period ratio less than 2.5.
You mean more planets here?
Yeah,
Okay.
right. So what kind of parameters do you have to change in your stochastic ratio?
So that's kind of that is a fine-tuning parameter. It depends on how long you let the simulation run. The longer I let them run, the closer they will get to each other. There's nothing that moves the planets apart from each other. They will always get closer. So the longer I run, the more skewed it gets towards
So when you stop?
Yes. How long?
Now it's different.
Okay. I wanted to show you a few things about seventh rings. And this is a slightly different topic, but it's actually related to what I just talked about right now, because it's an astrophysical disk. Okay. It is a disk, and it has a central body, so it's kind of like the solar system information, just a bit smaller. So you have to imagine this as the sun, and then planets forming in the disk around it. It's a small scale model of the solar system. I'm going to skip a few slides. What I'm going to do is I'm going to zoom in into one of those small regions here, so you only see a local patch of the ring, because the rings are really big, but whatever happens is happening on a scale of a few hundred meters. Okay, so I'm going to zoom in there. I'm going to show you a movie of the rings. So what you see is the shear. First of all, it's a shearing sheet. So you see particle moving here and here. That's just because we're co-rotating with one particle in the center. It's just the orbital motion that creates the shear. These small particles on top of the bottom, these are ring particles. These are IT particles up to a meter in size. You can think of them as dirty snowballs. They're constantly colliding with each other. And what creates the structure here is self-gravity. So it's gravitationally unstable, this disk. And you form wavelengths. This is a tumor wavelength. This is typically 100 meters or something around that scale. This is very similar to a protoplanetary disk if you think about it in terms of stochastic migration. Because the protoplanetary disk is going to be turbulent. It's going to be turbulent by the magnetorotational instability, not by the gravitational instability. But it's, again, it's a disk, and there's going to be some bumpy structure in the disk that moves around. So that's like a very similar system. So we can use the same equations to study the evolution of things that are embedded in this case than in the protoplanetary disk case. And that body in the middle, that blue one, that's called a moonlet. It's a propeller. That's what people call it because it creates a propeller-like structure. You can only see vaguely because I'm zooming in the simulation. And you can see that it creates a weight here and a weight on the bottom. It's the same kind of weight you get in the protoplanetary disk when you have a planet that's going around. Just here it's made from the moonlet instead of a planet, and the weight is made out of particles instead of gas. So this body will see these clumps that stream by. Okay? They will gravitationally interact, and they will make this body undergo a random walk. And you can see that the simulation is already running for a while. You can see that it's moving around. Okay? It's changing its orbit. And this is in fact the only thing that we can observe that is embedded in a disk in an astrophysical context that's changing its orbit because it's interacting with the disk. So it's a really nice test bed for all these kind of things that I talked about earlier. Because here we can observe it. One orbit is only 11 hours at this distance. So we can take multiple images with Cassini over several years, and we can observe it over many orbits and look how it walks.
So how do you treat interactions between the particles?
There's a hard sphere model.
You have some power distribution particle size?
Yes.
What's the, in this scale, the movie, what's the whole radius of the movie?
It's approximately exactly its radius. That's why you have all the structure. If the real radius were smaller, they would clump, then you would just clump the material together, you wouldn't see anything. If the real radius, if the density were much lower of the particles, then you would not see anything either because self-gravity wouldn't play a very strong role. So this is really the case for Hanno. And seven strings magically are exactly in the interesting machine. Yeah, so this is 50 meters in size, and the other particles are 100 meter or so in size.
And this is implemented in the shared sheet.
Yes. So these simulations are done with rebound, and you can do that by yourself. Maybe just a bit of advertisement. It's a collisional n-body code that you can download and use, and it's really simple to use. So let me try and do this in 1 minute. I'm not sure if I have the internet. Okay, it works. So you go to Google, you Google rebound code, take the first hit, you scroll down a bit, and you have to copy and paste this one line of code. You open the terminal window, you paste the line of code, and now it's downloading the code. It is hopefully downloading it, compiling the code, and now it's running the code. Okay, that's all you need to do. And now you have this shear sheet simulation running on your computer, it's visualizing in real time, and you only have to put in one big particle in the middle and run it for a bit longer, use more particles, and then you get the same simulation as before. So it's using a tree code in the background to run this. It's just okay, so these propellers. You can observe this orbital migration I mentioned before. And you can compare the orbital migration to what kind of forces are present, and it is in fact consistent with being a random walk. It's not quite easy to interpret the observations, but it is perfectly consistent with this idea of these things undergo a random walk. So this is our only example of embedded bodies orbiting in an astrophysical disk, and they undergo a random walk. Okay, so in the last part, a few minutes left, I want to talk about the Open Exoplanet Catalog, which is a project that I started last year. And if you're working with planets, you might ask yourself, why the hell do we need another catalog of extrasolar planets? There are already several out there. Why do we need another one? Well, I think there are good reasons for using another one, because I got annoyed by the other ones, so I made my own one. And here's how it works. If you go to any astrophysical database or catalog that's out there, it doesn't have to be about planets. It's really general. There are a lot of things that are not well done in my opinion. First of all these things are centralized. So there's one person that's in charge, or maybe a group at a certain university that's in charge of maintaining a certain list of hotlinks. And these people are, you can't contribute anything to it. Those are the ones who make the decisions, and you have to send them emails if you find a typo, if you want to make a correction, or if you want to add data. You can't do anything yourself. They're in control. Okay? It's a closed ecosystem. Everything is very centralized. Most of these things are web-based. Most of them are just a database put on a website, and you can download it and use it. In most of the cases, the website is not well written. You're restricted to do whatever the website allows you to do. It's just not the kind of environment that is very flexible to use. Most of them turn out to be fairly slow in updating the databases, or they're actually just outdated. And that makes sense because it's a centralized system. There's only one person in charge. It's a very popular database for extrasolar planets, which is maintained by a French person. And French people tend to have long holidays over the summer. So whenever there's a holiday, it's not going to be updated. It's not a criticism for any French people in the audience. But it's one of the problems that bothered me, because I wanted to have a database who always included the newest planets, but I couldn't add them to myself. Or I could add it, but then when he comes back, he will add it himself, so he does twice the work, and I have to constantly keep track of which parts I added and which parts he added, and it kind of gets a mess because I can't contribute to it. Also, what annoyed me are the kind of data formats that we use. People like really static tables. They're very simple and they're very easy to use, but they're very hard for this kind of data set, which is very diverse. In extrasolar planets, there are planets that go around binary stars. There are planets that have binary companions. There are quadruple systems with planets in there. It's hard to represent that in a static table. Okay? It's a hierarchical tree-like structure that you have. If you want to find an exomoon, for example, it would be very hard to include an exomoon into any of the existing databases without defining new fields for the exomoon and so on. If you want to do that in a better way, I'll show you now how to do that. First of all I'm going to say, closely related to some open source philosophy that's behind it. It worked really well for a lot of other projects, like the Linux kernel, where thousands of people working together to create something. And you can use the same tools and the same principles to create a catalog for astronomy. So everything is open source, everybody can use it, everybody can add to it, and everybody can expand it. Okay? This is hardly working so well because everything is based on Git. Git is this distributed version control system that you might have heard of. Mostly all open source projects nowadays use it, like the Linux kernel, for example. Any other one that you have running, probably all of them are using Git by now. There is no central repository for Git. Everyone's repository is equal. So if you have one on your laptop of the entire catalog, it's equally important than someone else's laptop. And you can put it on the server and host it so that other people can Google it and find it, but it doesn't make their copy less important than yours. Everybody's copy is equally important. And you can contribute to everyone's copy. Okay? So it kind of breaks up with this closed ecosystem. It doesn't mean that everything is open, but it allows people to be more flexible. If you have a close collaboration, for example, you're working on the Kepler team and you want to make an announcement of Kepler plans, you don't want to release them before a certain date, then you can share all the information within your group without releasing it to the public. And then at some point when you want to release it, it's very easy to push it to the public repository that everybody can see. That's all thanks to Git. The other thing is that I'm using a hierarchical value format. It doesn't really matter which one it is. I chose to use XML. You could use something else, but JSON or whatever you like. The thing is that these kind of more text-based descriptive files are really easy to use, and they're very intuitive to parse. There's no ambiguity in what column in which table corresponds to what, because you can just read it. I'll show you an example in a second. The sizes of these things are also very small. They compress really well. And for the exoplanet catalog in particular, so this is ready to use. All the exoplanet catalogs, exoplanets are in there. It includes all the information for all binary systems that I know of. It has all the triple, quadruple systems in there, and all the KOI objects as well. Let me show you one example of why I think this is so much easier to use, even if you don't care about the open source philosophy and that part. This is one example of catalog entry for one planet. And without me giving you any explanation, you can figure out most things about the planet. You can figure out that its mass is 3.8 Jupiter masses. You have to guess a unit or you look it up in the description, but in most cases you can guess what these things mean. You can probably guess if the mass of the star is measured in solar masses and nothing else. So just by looking at the file, you can read it by eye. You don't need to look at which column corresponds to which. It also shows you how you can exclude more data, for example, an exomoon, which is a bit arbitrary, but it works the same for binary systems. You would just add a new tag here for a moon, and then you would have a moon that is orbiting the planet, and you would not break your file format. You can just use the same scripts that you used to parse a file before. You would not break anything, you would just add more data to it. One more advantage of using this file format is that one entry corresponds to one line. You don't have to write it that way, but it makes sense. Because if you use git in the background, you can make a reference, and when you change something, you can include a reference to every single line. So if someone changes the mass because he thinks it's a typo, this change of this line will be attributed to the person who made the change. You can include a reference to a scientific paper for that specific line. So every single value in this file will be referenceable, for words, to the scientific paper where it's coming from. If you simply have a table, that's much harder to do, and you need a separate entry for each value that you add and say this comes from this paper, or this person made this entry at this time. This all comes for free if you simply write it in that and you use git in the background. It's also really easy to parse. It's not only easy to read, but if you use any programming language, you can very easily parse these files. Okay? This is Python, and it's just a few lines of code. And I don't even need to explain to you what this means, even if you don't know Python. You can see what it does. It goes over all the files, it looks for all the planets, and for every planet it prints the name and the mass of the planet. Okay? That's it. You can do many more complicated things. You can only find planets in binary systems. All you would have to do is write /binary/planet. Then you would only find planets in binary systems. It's really that simple to parse these files. Okay, so if you work on planets, go to the website and try it for yourself. The website is just the front end. This is important to keep in mind. What's really so this is how the website looks like, and you can do a lot of things like plotting correlation diagrams, or you can plot the correlation diagrams and change parameters. You can click on things and you get to the detailed page. But that's just the front end. What you should really think of it is, you should think of it as a database with just the files in, and that's what's posted on GitHub. These are really all the files, and you can access all the files, and you can change the files as well. You can make your own copy, you change it on your own copy, tell me that you made a change, and I will pull from it, and you will have the correct version up in no time, and you will be attributed to all the changes you add to it. Yeah.
So, Wikipedia is the general word Wikipedia, of course, is not a community party, as a typical scientist, but Wikipedia does need, needs watchdogs, right?
Yes.
So you think this can operate without a watchdog?
It works perfectly for the scientific case, I think. What would happen is that, let's say you make your database for extrasolar planets, you would make a copy of this one, and you would only trust people that you know personally, and you would import their data. So if I know you, I would take your catalog. If you know someone, you would take theirs. So by this one-to-one relation, you know all the people that make the contributions, and you would not allow some random people who randomly changes all the parameters, allow him to be hard. So it always depends on who you trust. It's the same for the Linux kernel. Nobody would download a random version of the Linux kernel from the internet. But you know Linus Torvald, for example, and his version is considered to be the most reliable one, and he knows certain people that contribute to his version. So it's the same way. You have to just think of it as a Linux kernel, basically. You know someone that you trust, you take his version, and if he trusts you, you can convince him to take your changes into account as well.
So there are like 10 million versions?
Yes, if you search for Linux, there are probably 10 million versions of the Linux kernel out there. Oh, for mine, no. For mine, there are maybe 20 or so.
10 million users, 10 million users.
Oh, so yes, they are not all contributing, unfortunately, so I have to do most of the work myself for that. But yes, there are about 20 people or so who actually made a copy that's publicly available, and if they make an addition to that, if I know the person, if I review the data, I will take it into my version. And if I make a change, they take my change and incorporate it into their version. And all this is based on Git, so it's very easy to push and back, to change it back and forth. And you can do it offline, you can do it on the plane. You can take a paper and your laptop, and you can enter the data on the plane. If you get off the plane, you push it, and then it's out there. So it's very decentralized. And it's not only for planets. You can think of any other astronomical database or structure that you can possibly think of that's very similar to Rein. I'll put up my conclusion slides and I stop here. Thank you.
We have time for questions.
How specific were your stochastic migration models to the disk? You mentioned you ran the minimum mass of the nebula, but did you, that's probably a different mode. So did it make it faster? Did you
Yes. Yes. The more the better. Yes.
So that's generally also.
I don't have to, so I'm using a fixed density of imaginary background, which is one of the shortcomings. I don't need an alpha of that out. But yes.
Do you begin to hit different resonances? Do you hit different resonances?
So you never get closer than a certain point. There's probably a physical reason why that is the case, but I'm not sure about it. So you only get to this kind of sweet spot here. You never get much closer. I would love to know why.
I see lots of measures and crossing screws.
So
So if I increase the migration rate, I can push the planets one to the other. And many times I've measured.
They might-
That's why I was asking about measuring.
okay. I've not seen that, but I might also not as much as miss it. I don't know.
It's interesting to know where that happens.
So you did have a different, I thought you did have different alphas in your plot.
It might have been, the alpha was,
Oh, is that something?
it was something different, yes.
Oh, okay, sorry.
It was the amplitude of the stochastic force.
Oh, sorry, okay.
Which is not the normal.
Yeah, no, I understand.
Something else.
Any more questions?
I'm curious about Sandy's ring. He says if you did the bars with the custom software and after.
So there's some. So what we learned is that it's not a perfect copy. There are some important differences, and one of them is that this is not a gas disk. This is probably the disk. So in normal gas disk, what you have is this gas pressure that supports you. That's not the case here. So the migration rate is different. You can't just use the type 1 migration rate for a normal disk because of this gas pressure which is moving. That's one of the things. The other thing is that it's really hard to interpret the observations, even though this is much easier to do. It's very hard to actually find out whether this thing is a random walk or whether it's not a random walk. If I show you the observations, this is what you see, and this is called a longitude residual. What you do is you take pictures of the object, and you expect it to be at a certain longitude in its orbit. But if it changes the same major axis, it will be slightly before or slightly afterwards. So it kind of is an integrated effect. And this integration that the orbit does is smearing out all these small-scale features. So you don't really see a random walk. What you see is very smooth. It almost looks sinusoidal. But this is exactly what you would expect if it's a random walk. Great counterintuitive.
The period has no physical significance, just
Nope, it has no If you observe it for twice as long, you will see the same kind of figure, just stretched for twice as long. The period has no physical meaning. Yes. Because there's, in the random walk, there's no time scale involved. It's just a random walk. This is very confusing. If you look at this, you can try to explain it because maybe some frequency inside this ring, some resonance, some other moon is exactly matching this frequency. First of all, it's not, but second, it's just an observational bias because you observe it for a fixed space length. You can subtract any linear function from this curve, and it will not change its meaning. It's like a gauge transformation if you subtract